Hi everyone. So I got this FPGA development board about a year ago, maybe a year and a half ago. And when I first got it, I was hoping to find some video tutorials that would kind of walk you through the whole process from start to end. And I couldn't find any, so I thought I'd make one today. So the project for this particular FPGA is really minimalist, just a HelloWorld type thing. Basically we have the development board, and there's 8 LEDs right here, and then I have a push button, and if I push down we have a binary counter that'll count up, and it will only count up when I hold down. So basically the push button is a enable pin. Anyway, it's meant to be a really primitive HelloWorld program. The goal isn't to make anything revolutionary. I just wanted to show the entire process from start to end. So I'm going to show how to use the Lattice Diamond software. We'll create a project. We will write the code. We'll write a test bench and simulate it to verify that things are working the way they should. We will program to the FPGA. You can program either to the Flash or to the SRAM. Programming to SRAM is a little bit faster, which is good for development. And then finally I'm going to cover Lattice Reveal, which is their logic analyzer tool. It's a pretty neat tool. It's really kind of overkill for this particular project, but I'm going to show it because when you start doing real stuff, it'll be really helpful. Let's find the MachXO2 Breakout board. So if you search for MachXO2 Breakout board, the first link will go to Lattice's website. And here's the product page. And if we take a look at it, we can see that there's the FPGA here. And on my board, I soldered some headers onto these pins, but they don't come with that. So that's actually kind of nice because you can solder components direct on the board, or wires, or however you want it. So you can buy it through many sources. I got mine through Mouser. They're pretty cheap, under $30. Other places have them too. DigiKey has them, several others. So first of all, let's find some documents that are going to be rather helpful. If you go down to user manual, or down here, the user guide, click on that. So it's a fairly short document, and it kind of covers what you would expect. It has a overview of what's possible, has a schematic, a bunch of other stuff. So at the very end, you have the bill of materials, you have the schematic, and then for this project, yeah, here we go. Okay, so on page 13, it'll tell you what pin numbers correspond to what LED. So we'll need that later on. You'll need the Lattice Diamond software. So if you don't have it installed, you'll need to download it. So you go to the Lattice Diamond webpage, download whatever version you need. It's a rather big download, so keep that in mind. Go ahead and run the installer, let it install everything, including all the drivers. After that finishes, the first time you start Diamond, you'll get a couple errors about a missing license file. And just click OK on that both times, and then a window is going to pop up where you can select the license file. And near the bottom of that window, it will tell you your NIC ID, your network interface card ID. And so you go back to the Lattice Diamond webpage, click on licensing, go down to the free version, and you would then type in your NIC. You type it in here, check that, click here, and they will email you the file. And so you put it in the installation folder, which will be by default the C drive, and then you go to LSCC, Diamond 3.6, and then you go to the license folder. And that's the file. You want to put it in here. Don't rename it, just put it in here. And I found that you then had to restart Windows. If you didn't and you tried to open up Diamond, it wouldn't find the file, and even if you showed it where the file was, it just didn't work. So go ahead and restart your computer and then open Diamond. And we'll start out by creating a new project. So you can click here, or you can go to File, New Project. Give it a name. I'm going to call this really simple project HelloWorld. Put it somewhere. I think I have it. I have all of my Diamond projects in a particular folder, and I'm going to go ahead and create a new folder called HelloWorld. That's fine. You then need to select what device you are going to work with. It's actually printed on the chip. If you have good eyesight, you can just look at it. But there's also it'll tell you right here on the product page for the Breakout board. It'll tell you what chip is on the board. So MachXO2 7000HE, speed grade or performance grade 4, and there you have it. So now we can create, or we can write the code. If you go to File, New File, Verilog Files, I'm going to call it Top. And then I'll go ahead and write the code, and then I'll explain it afterwards. Okay, so here's the code. Our top module is right here. It has an output, an 8-bit output called LEDs. It has a 1-bit input called pushbutton. We have a 1-bit signal called FPGA clock. The MachXO2 has a RC oscillator built into it, and we can access that through the OSCH module. It takes a parameter called nom_freq for nominal frequency, and I set it for 133 megahertz. I'm going to call my instance of it RC oscillator, and then it takes for arguments STDBY is standby, and I set it to 0, false, and then it'll output the clock on OSC, which I connect to my FPGA clock signal. So how did I know to use that? If we go back to, if you search for MachXO2, and if you go to Lattice's webpage for it, if you go to the documentation section and go down to application notes, there is the sysclock PLL design and usage guide. And there is a section for the internal oscillator called OSCH, and it is on page 28. So you go to page 28 and you have internal oscillator, and so you can see here they tell you what the parameters would be. You don't need to use that, so I left it out. These are the possible frequencies you can use, and they give you some VHDL code and some Verilog code. I just used a more compact form. Instead of doing def param, you can use the pound sign. Anyway, and so then I have a module that I wrote called slow counter, and I connect the clock to it and the push button and the LEDs. And in that module, we basically have a internal counter, which is a 32-bit number. We initialize the output byte, which would be the LEDs, to all ones, and that is because the LEDs on the circuit board are wired active low. So if you drive them high, that'll turn them off. And then I initialize counter to 0. And then on every clock edge, every rising clock edge, if the enable signal, which would be the push button, if it's high, I increment the counter, and then I copy the 8 most significant bits of the counter to the output byte. And I invert it, again, because the LEDs are active low. And so you want to run synthesize to make sure you don't have any syntax errors. And now we can go ahead with simulation. So if we create a new file, go to File, New, File, Verilog. I'm going to call it testbench. And I'll go ahead and write it, and then I'll explain it afterwards. Okay, so here's the test bench. I have a time scale of 1 nanosecond. I create a push button and LED that I can observe in the simulator. I connect them to my top module, which I instantiate as DUT, device under test. Usually you would do a test bench for an individual module, not your top module, but because it's so simple, I'm just going to go ahead and do a top level simulation. And then you have an initial block. I drive push button low. I wait 1000 nanoseconds, so 1 microsecond. I drive push button high. I wait 1 second. I drive push button low. I wait 1 microsecond. And then finish will tell the simulator that we're done. And so basically I'm simulating that shortly after power up we hold down push button, or we hold down the push button for 1 second and then we let go of it. And we should see the LEDs counting, and let's go ahead and take a look at that. So if we go over to file lists, well, first of all, save everything. Okay, so go to top, right click on it. Make sure that it is included for synthesis and simulation. And then on your test bench, right click on it and make sure it is only for simulation. And then you can call the simulation wizard. Either click here or here. Give it a name. Click next. Next. Appears I have a typo. Okay, line 19. I forgot a semicolon. Alright, we'll try it again. Okay, so this is how it should look. No red lines. click Next, and click Finish. Okay, so by default it will simulate up to the first microsecond. So it's going to stop at 1 microsecond. Go ahead and click the play button to proceed with the rest of it. And you'll see over here telling you where it's at. So picoseconds, nano, micro, millisecond. So it's currently at the 17th millisecond. So obviously, yeah, this is an incredibly long simulation. You wouldn't normally run this long of a simulation, but because I'm doing a top level simulation and we have a push button, you generally simulate for maybe a second. I'm going to let this run for a minute or two and let it maybe count up to 1/3 of a second, and then I'm going to go ahead and stop it prematurely and we'll take a look at it. Okay, so right now we're at about 310 milliseconds, or about 1/3 of a second. I'm going to go ahead and stop the simulation. And if we zoom to fit by clicking here, we can see that the LEDs have started to count down. Now, as you saw in the video at the very beginning of this video, the LEDs actually count up, but again, the LEDs are active low, so it'll look like it's counting down here, but they actually count up. And yeah, the simulation is probably not the best demonstration. You wouldn't normally simulate a second. That's kind of ridiculous, but yeah, sorry. Anyway, so that's kind of how you get things going. If you want to do more, you probably should. Okay, so we can close out of this. We don't need to save it. Let's go ahead and assign pins. So we have, in our top module, we need to connect to the real world. We have 8 LEDs and 1 push button. You can go to the spreadsheet view, click in here or here, and why doesn't that show what it should? Okay, top view. Probably need to synthesize. There we go. Okay, so yeah, make sure that you synthesize your top module again. And then in your spreadsheet view, we have 1 input bit and 8 output bits. So my push button will physically fit on the headers that I soldered to my board in such a way that pin number 3 is where it's going to. So you can type in pin 3, and basically I have it so the push button, when it is not held down, it's floating. There's no contact. When you push down, it'll make a connection to VDD, which is 3.3 volts. So we need a pull down resistor, but that's fine because it has one by default. So you can see here, you can change it, but the default of down is fine. And then for the LEDs, let's go back and look at the PDF for the breakout board. And so the first LED is pin number 97, and then we have 98, 99, 100. Okay, so we have assigned all of the pins. Although technically we're using 3.3 volt logic, you can leave these at the default of 2.5 volts. And obviously there's a whole lot more that we can do, but for this HelloWorld project, we really don't need to change any of those. So now we have assigned all the pins. We'll go ahead and save. If you want to look at reports, you might want to check some of these off. And then we have, for exporting files, you have a bitstream file and a JTAG file. JTAG is used for programming to Flash, and a bitstream is used for programming to the SRAM. I'm going to go ahead and generate both. So check everything you want, and then you can double click on export files, and it will automatically call any prerequisite parts. Okay, so it has done everything, and we have a bunch of green check marks, which indicates no errors. That's good. We can now program the FPGA. You can click here, or you can go again through the menus over here. So we're going to create a new project. I believe that's correct, but let's go ahead and do detect cable. And you'll see cable A and cable B. Always pick cable A. Click OK, and everything else should be fine. Okay, so for some reason it does not automatically fill in the device correctly. You need to pick the HE version. Operation, the default is Flash, erase program verify, which is fine. Go to file name, you click in this region, then you click on the three dots, and you want to find your .JED file. And it will be in wherever you created your project, and then it'll be inside the IMPL1 or implementation 1 folder. So double click on that, and we can then program it. So you can click here, which is the program button. Okay, so it finished. If you look down here in the output tab, we have operation successful. You can see that it took about 31 seconds to program Flash. So when you're developing, you don't always need to program to Flash. It'll be a lot quicker to program to SRAM. And let's go ahead and try that. So if you go to Operation, double click here, and choose Static RAM Cell Mode, and then choose Erase Program Verify. You'll need to then pick your .bit file. Click OK. Why doesn't that match? Did I change something? What? Okay, I'll try it again. Oh, okay. So I was in it. I guess it defaulted to a different folder, which was for a previous project. So yeah, make sure you're in the right folder. So go to IMPL1 and then go to your bit file and click OK. Okay, so and now we can click Program. All right, and again, it finished successfully, and you can see it took about 12 seconds, which is about half what it took for Flash. So at this point, we're at what you saw at the very beginning of the video. The FPGA works just fine, and you can kind of go on from here and write a real project and do something useful. But another tool that I wanted to demonstrate is Lattice Reveal. It's a tool that basically gives you a logic analyzer that you can embed inside the FPGA. And that's really useful for when you've done simulations and they work correctly, but in the real world, it doesn't. And of course, that always happens. So it's a really useful tool, and I'll go ahead and do a really primitive demo of it, which, again, for this HelloWorld project is really unnecessary and way overkill. But it's a good tool to become familiar with. You can use, like usual, you can click here on the toolbar, or you can go to Tools, and you start out here, and basically you need to tell it what you want to look at, and in this case I want to look at the push button, and I want to look at the 32-bit counter, the internal counter, not the 8 bits that go on the LEDs, but all 32 bits. So if you go to the design tree area, we'll go to counter, and we can go ahead and just drag and drop. The enable line is our push button, and we'll do the entire 32 bits of counter. And again, you can see here we have all 32 bits. And we need to tell the logic analyzer tool, or we need to clock the logic analyzer tool. And I'm going to use the FPGA clock. One thing to keep in mind, and this is really important, the sample clock for the logic analyzer, which in this case is FPGA clock, needs to run faster or maybe at the same speed, but it can definitely be faster than the JTAG clock. And on this development board, I believe they're using a 15 megahertz JTAG clock. And that's why I had to run the FPGA at a ridiculously high speed for such a simple project. I mean, obviously I didn't need to use 133 megahertz, but you can't do like 2.08 megahertz. So keep that in mind. If you use a clock that is too slow, you will get an error when you try to actually use the logic analyzer tool. So we've told it what signals we want to look at, the enable and the counter registers. Go over to the trigger signal setup tab. Trigger unit is basically what your trigger is. It's your trigger. Double click over here. We'll go to counter, go to enable, and click that arrow. Click OK. So we want to trigger on the enable signal, and we want to look at a rising edge. And then because your signal can be a bus with multiple bits, you actually need to set this to 1. And so, for example, if you were triggering on a signal that was a 4-bit signal, and you wanted to trigger on the rising edge of the two most significant bits, you would do 1100. So basically, a 1 indicates trigger on it, and a 0 indicates ignore it. But enable is a 1-bit signal, so just set a value of 1. And then trigger expressions are really powerful. I should really point that out because it's incredibly useful. If you go back to the Lattice Diamond webpage and go down to documentation and user manual, there's the Reveal user guide. And yeah, it's an incredibly powerful tool. You definitely want to read through this document. It'll kind of tell you how to do all of the useful things that I'm really just kind of glossing over. But yeah, so you can do rather complex expressions. And yeah, it's really useful. But again, for this HelloWorld project, we don't really need an expression. So type in TU1, which is our one and only trigger, and the identifier for our one and only trigger. And I'm going to go ahead and let it store in the EBR, embedded block RAM, and everything else is fine. So just to summarize, we are, I guess you could say, probing the enable signal and the 32-bit counter signal. We want to trigger on a rising edge of the enable, which is going to be when I push the push button. That'll be a rising edge. It'll go from low to high. And our expression is just that one trigger because we don't have multiple trigger units. You can add more here if you want. So that's pretty much it. Go over here and we have a design rule check. Click on that. And if we look down here, we have design rule check passed. And we'll go here, which is insert debug, and that will actually modify your project and insert the logic analyzer tool. Click OK. And we can then save the file. So I'm going to just call it Reveal. And click Save. All right, so we have inserted it into the project. I'm going to go ahead and save everything. We need to go ahead and generate our files again, and then we need to program the FPGA again. Okay, so that all worked. We have a bunch of green checks, which is good. Go back to the programmer, and obviously we're going to have the warning here because that file has changed since the last time. We just regenerated it. So we're going to go ahead and program again. Click here. Okay, so that succeeded. We can now use the Reveal analyzer tool. Again, click here or over here. And we need to create a new file. And I'm going to go ahead and call it, I don't know, analyzer. And click on detect. And that's good. So it matches what we had over here. So USB N2B and FT USB 0, very good. Click scan. And it found the device. Click browse. And choose that RVL file that we saved a few minutes ago, and click OK. And so now it says ready over here, and if you click the play button, it will say connecting, and then it will say running. And so right now our logic analyzer is running, and it's waiting for a trigger to occur. So I'm going to go ahead and push the push button. And we got our triggered waveform. So you can zoom in, you hold down Control, and then use your scroll wheel. And there we go. So let's go ahead and change, like in this column you can change the base. We'll go to hex. And I'm going to go ahead and zoom back out a little bit. And so we can see that the 32-bit counter was 0. I pushed the push button and it started to count up 1, 2, 3, 4, and so on, as you would expect. And if we want to trigger again, we can click play again, and it will say connecting and then running. I'm going to go ahead and push the button again. And here we have it. So obviously the counter incremented quite a bit more than we saw earlier because the triggered waveform was so short. But yeah, so it started out at this huge number and it increments by 1 every time. So yeah, this is a really trivial demo. I know that it's kind of ridiculous to do it on this project, but at least now you kind of know how it works. And yeah, it's an incredibly useful tool, and it's included for free, which is wonderful. Alright, so that's pretty much it. I hope you enjoyed the video. If you have any questions or comments, please leave them down below. If you know anybody that might benefit from the video, please share it with them. And if you are interested in FPGAs, hang around because I plan to do another video within a month or so on how to make a Delta Sigma ADC with this particular FPGA and a resistor and a capacitor. It's really simple to do a basic Delta Sigma ADC, and they actually work pretty well. So yeah, stay tuned for that, and I hope you enjoyed this video.